Hi, I'm Simon Guiroy. In this video, I will be presenting our paper, Improving Meta-Learning Generalization with Activation-Based Early Stopping. This paper will be presented at CoLLAs 2022, the first edition of the Conference on Lifelong Learning Agents, and published in the Proceedings of Machine Learning Research. In this paper, we tackle the problem that in meta-learning, early stopping typically relies on a validation set derived from the source data, with a potentially large distributional shift from the target data, which can thus lead to poor target generalization. Our goal is thus to improve meta-learning generalization by early stopping closer to the optimal early stopping time for the target task distribution. By pursuing these goals, we provide important insights, such that in meta-learning, the out-of-distribution generalization to a novel task distribution may be inferred from simple statistics on the neural activations of just a few unlabeled examples. And that, by detecting when the target and source activation trajectories start to diverge from each other, we can better infer when the target generalization is reaching its maximum. Based on these principles, we proposed activation-based early stopping, a simple and general early stopping method for meta-learning. Meta-learning algorithms typically aim to train models capable of generalizing to novel tasks previously unseen during training. In few-shot learning for classification, novel tasks typically involve classifying examples between classes that were not seen during training and relying on just a few labeled support examples to learn the task. And in few-shot transfer learning, the task may not only involve new classes, but examples coming from an entirely new input distribution or image dataset. Now, the problem is that early stopping in meta-learning is typically performed using a validation set itself derived from the source or training data. But this validation data may have a significantly large distributional shift with the target data, especially in few-shot transfer learning. And the end result is that using the validation performance for early stopping may result in a poorer generalization compared to the optimum. In this work, our goal is thus to improve meta-learning generalization by early stopping closer as possible to the optimal early stopping time for the target task distribution. However, there is no one universal optimal early stopping time for all possible target task distributions. Hence, one needs to have at least some minimal amount of information about the target problem in order to early stop. Of course, the model doesn't control how many new tasks will actually be presented, as there could be several thousands or very few, but by definition, the model will need to solve at the very least one task from the target task distribution. Otherwise, there is no need to generalize and thus no need to early stop. Therefore, our method will only use the few support examples of one single task from the target distribution. Moreover, our method only relies on unlabeled data, which accommodates for the fact that access to labeled data is typically more restricted. The intuition behind our approach is to analyze the evolution of the trajectory of the neural activations as training progresses to infer how the target generalization evolves over time. In deep learning, the feature extractor is responsible for learning deep representations on the data, often comprising the majority of the neural architecture. Hence, it makes sense that it is critical for the generalization performance. And to fully characterize how the feature extractor evolves as a function of the input distribution, we'll look at the activation distributions at all hidden layers and how they evolve over time. The core of the approach is actually to compare the evolution of the target and source activation trajectories, noting that if the target and validation accuracies peak at significantly different times, it means that the accuracies will first be positively correlated and then switch to being negatively correlated. And the intuition is that this should be reflected in the activation trajectories, such that they initially evolve in similar directions and then start to diverge. Our method can be broken down into three parts. First, we need to characterize the activation distributions in order to project their trajectories into some space. Now, one way we can do this is from the sequence of moments of their distributions, because under certain conditions, a random variable may be entirely determined by its sequence of moments, which is also true for multivariate random variables. But since we only have the activation vectors of a few input examples, We will not try to estimate higher order moments because it would lead to high estimation error, and we will only estimate the first and second order moments. But that still makes a lot of quantities to track and a very high dimensional space, so we will further aggregate across the feature dimensions. But before we do this, first let's notice that there are three discernible types of quantities here: the elements of the mean vector, the elements of the diagonal of the autocorrelation matrix, and the non-diagonal elements of the autocorrelation matrix. We will thus summarize those three types separately, and to summarize them, again, we compute their moments, this time across their feature dimensions. We thus compute the first but also second order moment of the mean vector, and for the other two types, since they are already of second order, we only compute their first order moment across feature dimensions since we want to avoid higher order statistics. And there we have it, a compact four-dimensional space. It is simple, yet general enough to express, by linear combination of these aggregated moments, many metrics on the distributions of the activation vectors. Thus, for a given input distribution, we embed the activation distributions into the space spanned by these four aggregated moments, and we do it at each layer of the feature extractor. We do this at the end of each training epoch, obtaining the neural activation trajectory. Okay, so for the second part of our method, now that we have the target and source activation trajectories, we need to find where in the neural network do they diverge. Thus, we select the hidden layer where the two trajectories show the strongest divergence. Now remember, earlier we said that if the target and validation accuracy peak at different times, they will first be positively correlated and then switch to being negatively correlated. Thus, our method finds at which layer and onto which hyperplane of our four-dimensional space there's the most negative correlation between the two projected trajectories, which by the way is fairly quick to compute. Also note that in the experiments of this paper, we simplified the method by only selecting which dimension instead of which hyperplane of the four-dimensional space, but the principle remains the same. The second part of the method does consist of finding what we call the critical layer and the critical moment. And the critical layer and critical moment may change depending on the setting, like which architecture, meta-learning algorithm, source, or target dataset is involved, meaning that one must look under the hood and consider all layers of the feature extractor, instead of just looking at the final representations. Likewise, the critical moment will also depend on the setting, so one must consider a space of functions instead of just one fixed metric. Finally, for the third part of our method, our algorithm finds, at the critical layer and along the critical moment, when does the target trajectory starts to diverge from the source trajectory, and thus, when do they start to become negatively correlated. Note here that we assume that target generalization peaks between t0 and t-valid, but not after, which we consistently observed across our experiments. Also note that the objective that Abe maximizes is defined in such a way that if no divergence occurs, for example, if the target problem is very similar to the source problem, then Abe will stop at t-valid and thus perform on par with validation-based early stopping, since we want to improve generalization when there are gains to make, but when validation-based early stopping is already performing well and there is no gains to make, then Abe should perform as close to on par with validation-based early stopping, and very importantly, almost never perform worse. So now, in order to show that the key principles and insights of our work are fairly general statements on meta-learning and out-of-distribution generalization, and that our early stopping method is generally applicable, we performed a large and challenging array of experiments across multiple meta-learning algorithms where we consider MAML, prototypical network, and matching network, three pivotal algorithms in the field, across several pairs of source and target datasets taken from the Meta dataset benchmark, and across different neural architectures. Our results show that Abe consistently outperforms validation-based early stopping, while it only relies on the few support examples, unlabeled, of a single target task. And these results consistently hold across meta-learning algorithms, source datasets, target datasets, and across neural architectures. Here we can see that Abe generally closes a significant portion of the generalization gap over the validation-based early stopping baseline. Indeed, if we look at our experiments a little bit closer, we can see that when the baseline has a significant generalization gap, as shown in red color in the top figure, then Abe, in the lower figure, generally outperforms it, as shown by the blue color. And, very importantly, Abe very rarely performs worse than the baseline, as shown by the red color in the lower figure. Finally, when the baseline doesn't suffer from a significant generalization gap, and there is no much gain to make, then Abe performs roughly on par with it, as shown by white color in both figures. And we consistently observe those results pattern across our experiments. Finally, since Abe uses data from a task of the target problem, we also compared it against another baseline that uses as well a task from the target problem. Indeed, there's an obvious question: can we simply estimate generalization to the target task distribution using the performance on a single target task? And here again, Abe is the clear winner. Okay, so if we summarize the key insights of our paper, we can say that in meta-learning, the out-of-distribution generalization to a novel task distribution may be inferred from simple statistics on the neural activations of just a few unlabeled examples, and that by detecting when the target and source activation trajectories start to diverge, we can better infer when is the target generalization reaching its maximum. Based on these principles, we proposed activation-based early stopping, a simple and general early stopping method for meta-learning. Finally, through extensive and challenging experiments, we show that Abe consistently outperforms validation-based early stopping by improving target generalization. Now for future work. First, we will investigate using the same core principles behind Abe to infer and improve generalization in other OOD settings such as continual learning, multitask learning, and domain adaptation. Furthermore, we will investigate how to extend Abe as a more general method for model selection, optimizing other hyperparameters than stopping time. This was Simon Guiroy. For any question, feel free to reach out to me, and thank you.